So today we're going to focus on categorical models. Now, I'm going to kind of go slow through some of this, especially when it comes to the code, in the sense of kind of going through some of it with you. The biggest thing that they sometimes don't take away from these types of modeling strategies that we have, because we're in some another world that basically we can refer to as either general linear models or maximum likelihood estimations. Those are a little bit two different things, but in some ways they're very linked. But the problem is that people don't kind of realize that or not roughly, but basically you can't focus just on the coefficients anymore. That's no longer as telling as it used to be. When we looked at OLS models or any type of, linear models, that we could basically, even if it was an interaction, we know that we could look and see information that comes straight from the coefficients. Even if we wanted to know the true effect, we know we have to combine things. The coefficients we could still use. Here, we have to take additional steps to actually figure out magnitudes. We can figure out directions directly from the table. We can't figure out the magnitudes directly unless you're a savant with doing that type of math in your head. Usually you need some additional stuff. So that's why I'm going to kind of go through it and kind of show you some of the ways we have to set it up to be able to show how you might go about looking at something, because also I should say that the space on how we get our answers is going to kind of expand a lot. It's no longer just one answer anymore. It's more than you can even think of. It's all going to be based on your choices on which point you want to estimate, or where you want the point of interest will be. Okay. So we're going to do binary models. I'm going to throw back into this information the linear probability model. It's just because we only spoke about it a little bit, but in some ways we can do a little comparison between these models and the MLE models. So we're going to look at interpretation, marginal effects. Sometimes I'll call this partial effects. I have a habit of going back, a bad habit of going back and forth. Looking at predictions and performance, because the R squared that y'all love to look at, no longer really here, not the same as what you think of the R squared. It's a different type of R squared. So these are all these little things that are changing. We can also look at categorical models. There's usually two types, general two types. There's probably more that I'm not as familiar with. But we have models that basically we know that the decision is there, but each of us might order them in a different way. We have preferences that push us one way or the other. So there's no social ordering system that we can all agree to. In terms of the order model, there are some that we could actually, order for whatever purposes that most people would agree on. So those take two different types of equations that we have, but we'll also look at those interpretations, the marginal effects, prediction, and performance again. These are the things that basically we're always going to focus on for these types of models, because it's just, you might have read about them, but probably actually being familiar with them would become with more practice with them. So you kind of read about them, but you don't really practice them. So you know some of the information, but how to do it might be just not completely there. Then we're going to look at binary categorical independent variables. So we're going back to the categorical right-hand side variables. But we want to I just want to give some information on interactions, which are going to act a little bit differently here. And then also marginal effects and looking at confidence intervals. So this is really stepping away from what you're used to in terms of OLS or any type of linear model like this. You run the regression, but that is not the last step. You're about 20% in. Then you have to work more to be able to get any type of answer when it comes to magnitude. Okay, so a lot of times with economic data, we have limitations. I've already sort of mentioned these before, but because they're observational and not, experimental, there's always errors in some ways. It's not something that we can take with, that was the measure I given, so that's exactly what it is. Measurement's not always continuous, and then also the data is usually not a complete set of all observations. It's some type of subset. In that case, we have to make certain adjustments on how we're thinking about these. So remember the other day I was talking about that wage really isn't a completely continuous measure because there is a cutoff usually at 0, unless you're willing to take negative wages and pay your employer. There's things that go along with that basically we can't see the entire set. There is some information that is unobserved. In that case, we can only do we have to make some modifications. Doesn't mean just because, we only see wages up to 0 or down to 0 that you need to change and not use OLS. I'm not saying that these are any better or you're not going to get any more information from the estimations. You might get some, different perspectives, but in general, when even the best applied econometricians, they're basically going to still use some version of OLS, even if there is something that's not considered a completely continuous outcome. Because again, it is the base. So we have the categorical binary distinct value. So we've already said that sort of with the LPM, but in here we'll be rehashing that a little bit. So these are yes, no, purchase or don't purchase. Sometimes in some surveys, we care about health status among the sample. Really bad, good health, really good health. Or it might just be something as, having a chronic disease, no chronic disease versus something else. There's different ways of looking at someone's health. But these, in this setup, is not set up for anything that's continuous. Not anything that we would typically want to try to predict the outcome on the left-hand side variable. And they're also non-symmetric distributions. Usually with OLS, we like normality. So that's why we like to push a lot of things to try to make it look normal. And then think about mean or variance. You have a yes, no type question. We have the mean value of the outcome, but what is that really telling us as much? 60% of the population said yes versus no. But it can be telling, but at the same time, it doesn't have the same direct meaning that we used to with a continuous outcome. Variance doesn't make a lot of sense either. So basically, it has some meaning, but it's just a different way of looking at it. And that's why we just have to change a little bit our perspective. And then we have the bounded from below and above. So this is a little bit away from the binary or the ordered or the multinomial. And here I'm just trying to give you some other ideas that I'm only showing you, in this case, I guess 3 to 4 versions of types of limited dependent variables. But in cases of wages, we think of that as being truncation, top coding. These are things that need sometimes adjustments in terms of how we analyze them. We need to take in account that there is a boundary. And you can do that. You can basically tell the program where the boundary is, and basically that gives you a probability, or I don't want to call it a probability right now, but some adjustments that we can make in terms of how we take away from the lack of information over that boundary. Okay, so there's just a lot of just adjustments that we make for those. We can also look at percentages, think about censoring or ranges of values not observed. Those are another case. The survey I've already sort of talked about top coding. Also, how many of you have ever used some type of variable that's a percentage as your left-hand side variable? Oh, usually a lot of people do that, so they investment as a percentage of GDP, something like that. But the point is that that's usually, without some strange outcomes, being somewhere between 0 and 1. So those are two boundaries there. You can't go below 0, you can't go above 1. That means in that case, you have to make some adjustments for those two boundaries. We even have some that I won't be talking about them today, but basically it's a fractional probit model. It's in the information of a probability model, but instead of being a 0-1, we're actually focused that it's somewhere in between those boundaries. Okay. Then we also have counts for positive integers. So this usually falls under something called a Poisson model. But I will tell you, well, I guess it depends on your area. But a lot of times what we're doing recently, at least in trade, is we're actually using the Poisson model in the same way we sort of use models for OLS. So under certain conditions, we could actually write this out, and it would have the same first order condition as we find, or very similar to what we find in OLS. And the good thing about it is we don't have to take logs. Remember I told you before we would actually destroy some of the data because it would be at 0. Here, the Poisson model can actually take on 0 values. And because of that, we're using this in trade a lot to take account that we no longer have to throw the zeros out. We don't have to use some strange modeling strategy to take in account that, we're throwing the zeros out because we like to log the left-hand side variable. At the same time, they're finding that under certain conditions as well, we don't actually have to treat it as a count. It can actually be continuous. So these are ones I'm not talking about today. I just wanted to kind of brief you on some of the ones that you can use. And these allow you to, to not make the assumption that the people at 0 are meaningless, or to try to increase everything by 1 so you don't throw them out. So that's one of the options that you have. Then you also can look at sample selection. Remember I told you the other day about the extensive intensive margin? We can actually model it by thinking of them as two choices. A binary variable or a binary model as the first choice. After you make the choice and we see that it's 1, or with some probability 1, we can include that information to help with the selection outcome. Because whenever you log an outcome for the next step, again, it's you're basically self-selecting and taking those people out. So we could actually bring the information back in after we've thrown it out. So these are all ones that I'm not going to discuss today, but it is ways of possibly maybe doing a little bit better job whenever you're doing the data to not just assume continuous outcomes. Okay, so yeah, just keep in mind I'm not really covering any of these. I'm sticking to everything above for the most part. And just to keep it general, I'm not going to go into a lot of the maximum likelihood theories or going into direct comparisons between it and GLM. It's better if we can just kind of grab the intuition of how we think about these things. So both approaches are going to rely on the same principle. We're going to choose parameters that make the observed data the most probable. This is why we're focused on the log likelihood. Basically, we're trying to move it from some negative outcome as close as we can to 0, because what that means is we're approaching 1. So the better we do, the closer we can get it to 0, usually means that it'll be a better likelihood that we actually observe that particular data set. That's what we're trying to do. We give it a data set, yeah, we're getting it to choose the parameters to try to give us the exact same information back. Okay? So the MLE selects those parameter values to maximize the likelihood of the observed data. Just keep this in mind, the probability direction is reversed. Rather than predicting the data from the parameters, we select parameters that best explain the data. Okay? Likelihood function depends on both the observed data and the assumed model. You see where I said that, assumed. This is where usually in OLS we would like it to be normal, but we technically, well, not technically, most times we don't care exactly what the distribution looks like. Here, your choice of, assumed choice of the distribution is going to make a lot of changes or differences most time. The only time that's not the case is usually in terms of probit and logit. At least away from the tails, they're going to be very similar for the most part because they're symmetric distributions. But usually around the tails, you might get something a little bit different. So just think about this also as a different sample would lead to different estimates and a different likelihood. You run your data to say 2024, you get some outcome. As soon as you update that, say, to 2025, it's a new complete data set. It's not the same. That means you can get changes. We would hope that wouldn't be the case, but it is possible. Okay? Because it's using the data at hand, and this is a new sample. You're giving it by adding a year. Okay? So just expect that the little tweaks are going to change your outcome sometimes. Hopefully, again, not dramatically, but it can happen depending on certain how the data is structured. In nonlinear models, sort of already pointed to this, parameter magnitudes are not marginal effects. What I mean by this is that the coefficients that you see without context is meaningless. Okay? What I mean by that, if we assume a probit model, we'll get more into this in a minute, basically that coefficient is adjusting the z-score. Unless you have the whole normal distribution z-scores in your head, that means you have to take those z-scores, and that then changes the probability. Okay? So that's what I mean by earlier when I said you run the model, first step. Now you have a few more steps to do to actually find out the true effect. In terms of the logit model, that's going to be any kind of coefficient is going to be changing or an adjustment to the log odds ratio. Okay? So these are not something that you can just feed off and look at what's going on. There are some programs that actually will show you the marginal effects in the tables. My advice is not to use those. Why? Because basically learning how to actually do the calculation is going to be best for you, because those programs typically are set to give you two types of outcomes. One is referred to the average treatment or the average marginal effect versus the marginal effect of the average. Those are not always the most interesting points that we can actually look at. So that's why I'm saying it's better to sort of give an idea and know how to actually go about the calculations. So once we do those additional steps, or the required additional steps, we can actually start to interpret what the effect is. Okay? When the models are correctly specified and the sample size is quite large, we need asymptotics here. Then basically the estimates should be consistent, asymptotically normal, asymptotically efficient. You notice I haven't really talked about anything in terms of endogeneity because it's better to not bring that in yet. Those are unneeded complications just to learn about the models. But once you actually start using models, you need to actually consider those things. Okay. Okay, so that's sort of where we're going today and how we'll sort of be thinking about these models. So we're going to start off with the binary dependent. Most of, you've kind of said that you know a little bit about those models. The ones that we focus on typically are going to be the logit and probit. Those are not your only choices. Okay, these are symmetric distributions, but there are additional ones that are considered asymmetric. Sometimes, we like symmetry, but at the same time, our data is probably not going to be exactly symmetric a lot of times. So we have to think about different ways of, well, it's just a additional type of way of analyzing to allow it to where it's not considered to be symmetric. So when we're thinking about this, we're going to think about the complexity of human choices. That's why we sometimes call these choice models. Usually if we're referring to the choice models, we're typically they like to usually throw just the logit in there. But like I said before, the probit typically is going to be very similar to the same results. So individuals make numerous decisions daily, often involving complex factors. However, these choices have to be simplified into a binary outcome because I can't see things that may be determining why you're choosing that particular choice. So these are basically constraints on my amount of information I know about you, or just the nature of the decision. So you've all been through classes that basically talked about utility. Meaningless for the most part, in the sense that we use it as basically, higher utility and it's higher than the cost of good. We make the choice to actually do the action. A lot of times, there's no way I can actually figure out what a utility is or a measure that you have, but I can observe whether you choose something or not. So we use this some people have used this in research on consumer choices in grocery stores. I basically can see who's making the choices for what types of goods, and then from that, I can then try to figure out what coupons I should be bombarding you with in your email. Yeah, that's why they give you that little card, by the way. They're basically figuring out things about you. I don't know if they're using these models, but the thing is that they're seeing the choices that you're making. That's why whenever you purchase something, the next day you're getting a coupon for that in your email. So these are the things that we're going to be kind of stuck with, but we can kind of push the information from the 0, 1 outcomes to something based on your characteristics to figure out the probability that you're actually going to make that choice. Doesn't mean that you make the choice. It just means given those characteristics across the people that are very similar to you, what's the likelihood that you might make the choice? Okay, so we're going to be not stuck, but we're going to be having 2 types of outcomes. Choice equal to 1 indicates action or success. Just to keep that as simple as possible. I know that usually sometimes it's not about action or success, it's about whether you have something or not. But this is generally how we started out. And then we have 0 indicates the lack of action or failure. Okay? So in terms of the binary, we can think voting for a candidate or not, buying a product or not, accepting a job offer or not. These are your choices that you make, but at the same time, remember that we have covariates that are basically trying to give me information about where you live, education, general income. These are all helping me figure out the probability given those characteristics, what's the likelihood that you might make that choice. Okay? Understand the factors that influence the binary decision is crucial, basically predicting outcomes and making informed decisions. So we think about it in terms of economic factors, social factors, and psychological factors. Okay? This is sort of what we're using when we see surveys. That's one way of doing it. Other times, you've seen models in terms of Becker's crime example. These are all things that basically we're trying to figure out a way of predicting the probability that a person does something or not. Basically, we're going to be using these three factors or other things about our right-hand side variables to basically try to predict probabilities of us observing a successful outcome. Okay. So I wanted to give you an example. In this case, I just went through and found one of the you don't understand how many data sets that are basically available for you to basically try out techniques before using them on your own data. Basically, I went through one that a data set that I basically was just looking for one that had a 0-1 outcome, and it ended up being something about spam emails. Okay, so is it possible to predict whether an email is spam versus not spam? So it's going to sound weird, but spam, if you identify, will be considered success. Not spam, 0, failure, if you want to think about it that way. So we're going to be looking at several determinants. I'll show a bigger picture on the next page, but basically seems relevant given the number of emails everyone receives every year. I'm in here every day. When I get to my office, I have 30 emails. 3 of them might be worth even opening. Okay? And it's just something that we have to deal with on a daily basis. In this case, do spam filters actually use techniques to try to identify do they use certain characteristics within the emails to try to identify whether something is spam or not? Because we've all been there to where somebody sends us something and it gets thrown into our spam filter. You know, it's doing decent job most time, but sometimes things get thrown in there for whatever reason. And so is it using similar techniques? It's probably using something a lot more advanced, but at least it might give us an idea how it might be making these choices. So in this case, we have several things that are going to be used as descriptors. So remember, spam is an indicator. It's going to be 0, 1. 1 if spam, 0 otherwise. And then it has a number of different characteristics we could try to use. So was the email sent to multiple recipients? Is it from message listed as from someone, default for outgoing emails? I didn't think I chose that one because I wasn't sure exactly what that meant. CC, number of people CC'd, sender sent an email in the last 30 days, time it was sent. I didn't actually check this, but it might be interesting to know if it's sent in the middle of the night. Certain images, attachments, a bunch of $signs saying you're going to get rich. Winner, you know, we always have that one, the lottery winner. Claim your prize. And your inheritance, you always have that one. My uncles are always dying. I don't know how I have a family tree at all. Viagra's in one. Password. Number of characters. Line breaks. Formatting issues, and a few other things. Oh, I love the exclamations in the subjects. That usually goes with the inheritance. And then basically, there's a few other things in here. But you can see that given that we have a 0, 1, we can put all these characteristics in there. They're going, you know, yes or no's. But basically, we're going to run a model that tries to find the parameters that best or improve the probability of actually observing spam in this case. Okay? So if we were to actually put this on a plot, and we were just thinking about the number of characters. In this case, this includes letters, numbers, symbols, and spaces. Okay? Looking at this, it's hard to even pick out anything, right? So this would be not spam. That would be spam. We actually see that the number of characters typically is a little bit larger for those that are not spam. Your friends have a little bit more to say to you than here's your inheritance. You know, they're going to try to actually discuss, they're actually going to say, you know, how are you doing? Using your name and not just, you know, it looks like it's hi, and, you know, and that's it. You know, there's going to be some things that are in there that are going to be telling. But at the same time, that might still be able to pick out certain things that basically, this seems kind of weird, but there does look like there's a patch, at least this way, that these tend to be shorter. They don't want to spend a lot of time chatting with you. They just want you to click on whatever link they put in there to get you to go wherever. Okay, so that's one possibility. But the other thing that we need to look at here is, do you remember what the R squared is, what its purpose is? It's basically saying how well does my linear prediction, the line that I can draw, fit all my outcomes, right? We usually have a lot of dots all over the place and the line's trying to go through it as best as possible. Sometimes it's nonlinear, so it looks a little strange. But the point is that imagine looking at that here. These are the only reason there's a lot of things are I use something called jitter just so they don't all line up on the same line. But they're still all zeros and always one. That means I hit one point here, I hit one point there, everything else is missing. This is what I meant before, that your R squared is going to be meaningless, the one that you're used to, best fitted line. Okay? Because it doesn't fit unless it's straight, which doesn't really tell us a lot. So that's why we're going to make an adjustment on how we see the R squared. We're going to have to think about it just a slightly different way in that case. Okay? So that's with the number of characters. I could also look at it in terms of the number of characters as well as the number of line breaks. Okay? I could do this over and over and again, but it's not going to be as telling. Each one of these is only on one particular dimension. Remember, we have a lot of descriptors here, so we need a little bit better way of doing this than just here's my relationship and then trying to figure out, you know, the lines. In this case, these are just density. So basically the purple density here is not spam, and these are spam, I guess the pinkish or dark, yeah, I'll go with pinkish. So basically you can see in these two characteristics that basically they like them to be short and to the point. They have thousands of people to scam that day. They don't need to spend a lot of time on you. So that's basically why we have very few characters maybe, or very few lines. And I'm just guessing. I don't know if that's exactly always true. This is sort of the data that we're going to be sort of looking at. We have a 1-0 outcome. And then we have a bunch of characteristics that then we can sort of figure out where these actions are happening the most. And we'll do that with the models will be doing that for you. It's a lot easier that way. But before we do there, I just want to go back to the LPM. I know I'm pushing this a lot, but I just see so many people focus so much on the harder type systems that sometimes if we just need a quick, easy answer just to figure out whether we can do this or not, sometimes the LPM is not a bad way to go. So in terms of the linear probability model, remember that basically it's still the same setup as we would see with OLS, but it's just that the dependent variable is a little bit, it's no longer continuous in our case. We're basically saying 1 if the action occurs with probability P, and 0 if it otherwise, or with probability 1 minus P. In terms of the variance, we know that it's heteroscedastic, so we just have to make a slight adjustment to the heteroscedastic errors. And in this case, it's actually easier to not use robust in this case. We actually know exactly what the heteroscedastic errors look like because they're based on the probabilities. So basically, we could set this up and create our own GLS with this. Marginal effects, again, like I said before, are always constant. That means you could end up outside of the 0-1 type of probabilities that we think of, which that is one of the things that people start yelling about most of the time, that, you know, you predicted a probability greater than 1. Well, okay, well, I'll just change it back to 1. So if it's not too many outcomes, then if it's like 1 or 2, why not just adjust it back down? If it's below 0, why not just adjust those few observations up? Now, I know I said something about not dropping, but you could also drop them. You're going to find there's not much difference in the overall outcome. And then in terms of the marginal effects, in terms of dummy variables, basically it's going to be the exact same between the two. The reason I'm putting this here is because I'm going to show you later on that this no longer applies in the MLE world. These two do not equal each other. Okay? So we actually have to do 2 different techniques depending on what the characteristics of the independent variable is. Okay? So I typically do this, and then somebody that does a lot of econometrics yells at me. Basically, if it's not linear, who cares? You know, I know this isn't linear, really, because 0, 1, but on average, it's going to give you very similar outcomes, at least at the average, either the average marginal effect or the marginal effect of the average. Okay? So yeah, always keep that in mind, that you might be making your life a little bit harder than it needs to be. So if we were to visually look at the original one, the one I was showing before, basically looking at the observed spam, yes or no again, and then looking at the fitted probabilities from that outcome, basically I could say that, you know, this is bad in some sense because my mean is actually, or the min of my predictions is negative 0.15, but it's only a few of them. So I could definitely push them back up. And I'm not sure exactly how, usually this isn't the case, but somehow my top outcome for my prediction actually ended up being 1. That's usually a little strange, so it's probably like 0.999 something. But basically, again, we only hitting 2 points, but we're going to find out basically that later on that the average marginal effect and the marginal effect of the average is going to be very close to what we get in terms of the LPM. As long as we only care about the average. If we care about somewhere else, that's where it gets really, we have to do a little bit more work on our, instead of just using the LPM. So should we worry in this case? I just want to make sure that I'm covering all my bases before you said that he said you could go do that. Okay, if you're a pessimist, it's a bad fit. The estimates are not, or they're linear, so that means that, you know, we don't think about probabilities being linear. So that seems like a pessimistic way to look at it. And then the marginal effects are not going to be exactly right, especially as we move away from those averages. Optimist, basically the conditional expectation function property tells us it'll still be good at the mean. Okay, so that's what we care about. That's how it is. If you just want to be somewhere in the middle and don't want to take a side, basically just pay attention to how it's used. And be upfront about it. Okay? So that's my little spiel on, you know, this stuff. The nonlinear side of this, though, is the outcome is either success, spam detected, or failure, not detect, or not spam, or failure not to detect. Basically, we only have those exactly 2 types of outcomes. Doesn't really align with the previous methods that we think about in terms of OLS. Remember, we have first order conditions that then we can then take into, you know, well, we take the objective function and basically we can do calculus. Okay? The problem with what we have right now is from these pictures is we have a discrete jump. You're here or you're here. Calculus doesn't like that most time. That's why we have to make a little bit of an adjustment. Okay? So we can think about this as being a Bernoulli maximization function for a random variable. Basically, we have some probability that we view yi equal to 1. And then we have the opposite in terms of probability of 1 minus that probability, and then 1 minus yi. So in this case, we're taking both sides. And when we do that, and we look at the expectation, we'll see that basically it depends as 1 times the probability that y is equal to 1 plus 0 times the probability that y is equal to 0. This section falls out. That's why earlier when I was saying it depends on the probability of success, that's how we're always going to discuss the expectation. Any way that we're talking about the marginal effects, we're talking about this is a decrease or an increase in the probability of success, of observing that particular outcome, or of observing one. Okay? And we can rewrite this. I'm just writing this in sort of general terms. Sometimes I do have a little issue in my slides. Sometimes I'll do the proper math for expectation probability. Sometimes it'll just be E and P. Sorry about that. But they mean the same thing. So what's going to happen is we're going to be looking at the expectation of our binary yi given x is going to be equal to the probability of success given x, or covariates. And what it's going to be is some function g. Right now we're not going to define g. We're just going to leave it as is. But g is going to take in the function, or the linear function, that we're typically using with OLS. What I mean here is that we have a constant plus beta 1 times a covariate plus beta 2 times a covariate and so forth. So this is what I meant by we're going to be taking a little bit more time to actually figure out the effect. Because one of the things we're going to need to do is we're going to need to calculate this and then also know whatever assumption we make to feed it into a particular function. This is what I meant earlier when I said that that coefficient is going to adjust the z-score. We assume a normal distribution. We're in the probit world. Then basically that's affecting the z-score. If we're in the logistic, basically that coefficient is affecting the odds ratio, the log odds ratio. Okay? Those assumptions are typically not critical as long as you're at the means. As you get away from it, if you remember what the distributions look like, basically we get larger tails for one of the distributions over the other. But so we're only going to get differences in the tails for the most part. Okay? Right now, the way I'm looking at this is we're going to talk about how we're setting up the G here in this case. But everything that I'm going to speak about it in terms of the logit, but everything that I'm going to talk about other than the assumption, the functional form of the model, or the G in this case, the function, is going to be the same. How we go about estimating, how we go about all of our steps are going to be exactly the same. The only thing that we're actually changing in this case is either G is a standard normal or either it's a logistic. Okay? But it just helps me to keep it in one, so I'm just going to talk about it in terms of the logistic. So linear functions of the determinant are transformed using what we're going to focus on, something called the link function. Basically, remember that we have something that we've already said is in 0, 1 outcomes. Not anything that we can actually say would be close to what we're thinking about in terms of OLS. Well, what we need is something that allows us to take a linear version of that of our model and then take it back into something that we can actually use, or that we can actually start to use calculus with. In this case, we're looking at something that links our linear function, I've already said, here, with something that puts it in this outcome between 0 and 1. Basically, we need to transform this binary from y to something that is continuous, at least within a certain bound. Okay? In this case, between 0 and 1. Okay? So that's what we're going to focus on in terms of the transformation. So for the logistic function, we call it basically the logistic link function. And if we assume that, then basically we can take any linear version that comes out of our particular model and put it into something that is continuous, exponentiation of the x beta over 1 plus exponentiated x beta. Okay, so that is the link function. Once we do this, this puts it into something that that is considered continuous. Okay? And this would be the CD, that should be CDF, sorry, of the logistic function. So when we're thinking about economic theory, remember I was telling you that basically we see that you purchase something versus not purchasing something? Then basically, this is where we kind of link all this stuff back to utility. Basically, we're going to see some linear version of your outcome and characteristics that predict whether you're more likely to choose to purchase the good, or basically a probability of success. Okay? And this is how we sort of link back from utility into something of just making a simple choice. Again, I can't see your utility, but I will be able to predict with some probability whether you will do something or not. If I'm right, then basically it's saying that your utility for that particular good was high enough over the cost. I don't know your utility, but I know the cost of the good, so I can start to pick out information. Okay? So assumption about the probability distribution gives structure. So that's what we're doing here. If we assume something about G, or whatever the function is, the link function, then we can add structure to our outcomes. Okay? That's why we call it the link function. So, and then generalized linear models basically extend what we usually think of in terms of our linear regression models into these linear, into the response distributions using these link functions. That's why we refer to it as the general linear models. Basically, it's just that we're doing a little bit of a tweak after we use the estimates, and we take the linear function and push it through that link function to get our probabilities. Okay? So like I said, I'm going to stop here because what I want to do is sort of show you some of the code for these things, of the tables we're producing. These are not the final answer. Remember I told you that once you run this, you're about 20%, 30% in. Then we're going to kind of go into the additional stuff after that. But at least I want to show you the functions of how the packages and things that we're going to use to actually run these models. Then we're going to kind of take it on a little step-by-step approach. Okay?